Okay, this is lesson 10.3, probability, part 2. In this lesson, we'll be looking at several probability event types and how to calculate their probabilities. So, first one, mutually exclusive events. So consider two events, A and B. They are mutually exclusive if there is no common outcome in both events, or both sets. Nothing in common between them. Here's a Venn diagram that kind of shows you what we're talking about. So these are two events. There is nothing in common. There's a visual for this. These are called mutually exclusive events. Here, where they overlap, they have something in common. So this is non-mutually exclusive events. And again, the overlap means they have something in common. So what is the probability? The probability of mutually exclusive events, so if A and B are mutually exclusive events, then the probability of A or B occurring is the probability of A plus the probability of B. And the probability that an A and B occurring is 0 because there is nothing in common. So when this one right here, what's the probability of A and B? So that would be this right here. Anybody in this little region right here is in both A and in B. And so then mutually exclusive, that is a 0. The complement. We need to know what this definition means. The complement of an event is the set of all outcomes in the sample space that are not included in the event. So if event C is the complement of event A, then the probability of C occurring is 1 minus the probability of A occurring. So if this is A, the complement of that is everything that is not in here. So everything else, everything in B, everything out here in this region, all of that would be C, whatever is not A. Since probability, the most you can have is a 1, that's why it's 1 minus that. What's the probability of non-mutually exclusive events? So that would be this one right here. In this scenario, the probability of an A or B occurring is the probability of A plus the probability of B. And since we counted this twice, once when we counted A and once when we counted B, we have to subtract one of those, and that's why you see a minus. And then subtract the probability that it could be one of something in here. So these mutually exclusive event probabilities and non-mutually exclusive event probabilities are these right here. Okay? And then complement. So here is a little example. Down here so you can see it. You're going to roll a standard die one time. Let E represent the event that you're going to roll an even number, and let T represent the event that you'll roll a 3 or a 5. What is the probability that you will roll a 3 or 5? And then let's take a look at it. So what's the probability you're going to roll an even number or roll a 3 or 5? So what is the probability of event E or event T occurring if I roll a die? Well, E in a visual representation is 2, 4, and 6. T is 3 and 5. So the probability of event E occurring is 3 out of the 6 possibilities. The probability that event T is occurring is 2 out of the 6 possibilities. So adding those together gives me a grand total of 5 out of 6. Which makes sense. The only number that is not included is the number 1. Okay. What's the probability of event E and T occurring? What is the probability that I'm going to roll an even number and a 3 or a 5? Well, that's an impossibility. 3 and 5 are not even, so there's no way that I can roll an even number. I'm only going to roll one number. It's either going to be even or it's going to be an odd. And 3 and 5 are odd. There is no way that's going to occur. Okay, so this is the first glimpse into these things. Let's look at another example. So I have a box. that contains 100 balls. 30 of the balls are purple, 10 are orange. If you select a ball at random, what is the probability that you will select a purple or an orange ball? Okay, so first thing you want to look at is this mutually exclusive? So in other words, are there any purple balls that are also orange balls? And the answer to that would be obviously no. So we can see clearly that this would be a mutually exclusive event, which means the probability of a purple or an orange ball being chosen is the probability of purple plus the probability of an orange. And the number of ways I can get purple is there's 30 out of 100, so that'd be 30 out of 100 total. And for the orange, that would be 10 out of 100. And so when we add that together, you get 40 out of 100. And then you reduce your fractions down, which is 2/5, or as a decimal, 0.40. Okay. What is the probability that it is not purple and not orange? Okay. So that's literally the complement of what we just found. So the probability of purple and orange, well, the complement, if it's not purple and not orange, then it's not in this. And so therefore it is the complement. So it'd be 1 minus the probability of a purple or orange. And so this would be 1 minus 2/5 or 3/5. You can also go directly. If it's not purple and not orange, then that would be 40 balls that are purple and orange. That means there are 60 of them that are not. And so it'd be 60 over 100, which reduces down to 3/5. Okay. So, or it would be 60 over 100 or 3/5. So you can go directly to it if you can see all of the possibilities. Here's another example. So we have a skydiver. Let's see here, I got a picture. So we have a skydiver. He's equally likely to land at some point in this rectangle. Okay. There are 2 overlapping circles, circular targets of radius 5 meters on the field. To the nearest percent, what is the probability that the skydiver will land in one or both of the circles? So basically, I want to know the probability that it's going to land here in these circles. If it lands here, then it's in both, or here, it's in either one. Okay. So to do that, this is an area probability. So we need to find the area of everything. So what is the area of the field? Well, the area of the field is length times width, so it'd be 20 times 30, or 600 square meters. And then we have 2 overlapping circles. So we have, what is the area of a circle? The area of a circle is pi r squared, and r is 5. So this would be pi times 5 squared, or 25 pi square meters. I have 2 of those. Okay. And then the overlap, they've already told you, would be 30 square meters. So what's the probability it's going to be in A, if this is A, and this is B, then what's the probability of A or B occurring? Well, it'd be the probability that it lands in that circle, or the plus the probability that it lands in that circle, minus the probability of the overlap. The probability it lands in this circle is part over the total, so that'd be 25 pi over 600. And for this one, same thing, 25 pi over 600. And then this right here, they told you this overlap is 30, so it'll be minus 30 over 600. And so then you work this out. That's 50 pi minus 30 over 600. And then you should use a calculator, and you'll get 0.2118. And it said to the nearest percent. Percent is 2 decimal places, so 21%. Okay. provided everything is equally likely. Okay. So the next question we have comes from this. How can a Venn diagram help find probabilities beyond what we just basically were doing? Okay, so here's a new problem right here. So at Washington Union, 54% of the students are girls and 62% of the students play sports. Half the girls at school play sports. What is the probability that a student chosen at random is a girl or plays sports? So how do we do that? Okay. So a lot of percentages are floating around here. Okay. You can use a Venn diagram to help us figure this out. So let's put in some information that we know. So what a Venn diagram basically is you start off with a rectangle. This represents everything that is possible. Okay. And in everything that is possible, we have two topics here, which are girls and sports players. Okay. Those are the two items that we're looking at. So this event is the event for girls. And so the next event is going to be for sports. And so the question is, are there girls who play sports? And the answer is yes. So I know there's going to be an overlap. So this is sports. This are girls who play sports. This is girls. So this piece over here, that's not the overlap part, okay? In the sports realm, these are all the boys who play sports. Okay? Remember, these are all the girls. These are just the boys who play sports. So everything out here would be pretty much just the boys who don't play sports. So we identify what we have, and then we put in what we know. 54% of the students are girls. 62% of the students play sports. Okay? And half the girls at school play sports. Well, what is half of 54? Half of 54%. Okay, and you can work that out. So what is 1/2 of 54%? And you're going to get 0.27. This is where the girls who play sports. Half of the girls play sports. So this is 0.27% of the girls play sports, which means this is the other half, the girls who don't play sports. Okay. They told us that 62% of the students play sports. That means boys and girls. And if that is the girls who play sports, then how much of that 62 is left over? So 0.62 minus 0.27 gives me 0.35. So this is 0.35, the percent of boys who play sports. So if I add all those together, okay, if I add all those together, what is left over? Okay. So 54 plus 35, that is 89. If I take that from 1, I'm going to get 0.11, and that means 11% of the boys don't play sports. That's this part out here. So you filled in all the pieces. You have every part of the circle overlapping and everything, and then you have the outside region here of what's left over as a number, and then you can go through and answer all the questions. What is the probability that a student chosen at random is a girl or plays sports? Okay, so that is the probability that I have a girl or plays sports. That's the probability that we have a girl, plus the probability that they play sports, minus the probability that is a girl and plays sports. Okay, so what's the probability that a student chosen at random is a girl? Remember, that's the whole circle, so that is 0.54. What's the probability they're going to play sports? That's the whole circle. That's 0.62 minus the overlap, which would be 0.27. Okay? And we already know what the answer is because we kind of already found it. It's 0.89 or 89% chance that a student chosen at random will be a girl or play sports. So the next question I asked was, what percentage of students play sports are boys? What percentage of the students who play sports are boys? So this is a kind of a different question. Notice I'm not asking you the probability. So what percentage of students kind of refers to a ratio, okay? And so to do the ratio, I need to know the number of boys in sports, okay? So ratios are basically part over total. And so then the other part is, what's the number of students in sports? So that is the percentage of students who play sports are boys, okay? So we're just looking only at the students who play sports. So we need to know that total. Well, down here, the number of students that play sports, we were also told that 62% of the students play sports. So the bottom part is going to be 0.62. And then what is the percentage of boys in sports? Okay. Oops, here it is. Remember, this is the girls. The overlap is the number of girls, the percentage of girls in sports. So this is the boys in sports without the overlap. That's 0.35. And so then this is 0.35. And then you can use a calculator here and get this answer as 0.5645 or 56.45%. Okay. If a student is chosen at random, what is the probability that this student is a boy who does not play sports? So what is the probability that a student chosen at random is a boy not in sports? Well, we've already calculated all that. This is the number of boys and girls in sports. This is the number of girls. So everything outside of that circle right here are the students who do not play sports. And I only wanted to know the number of boys who don't play sports. And that is this number right here because that's the girls who don't play sports. This is the boys. It's straight up, that's my answer, 0.11 or 11%. So we already have that number in our Venn diagram. And that's why it's useful to use a Venn diagram to help us answer some of these questions. Okay? Let's look at another example. All right. Oh, before I do that, you can't answer it yet. We need to know something else first, and that is this. A new type of event, the independent event. Two events are independent if and only if the occurrence of one event does not affect the probability of the second event occurring. The probability of independent events, okay, the probability of A and B is probability of A times the probability of B. Okay, so a lot of times people get this confused with the one above and all that kind of stuff. This is two different types of events. So how are we supposed to get them straight? Okay, here's one of the reasons, the way I do it. So it's about the actions that are occurring. In mutually exclusive events, what I have is I have two events and I'm making one choice. So I'm doing one action. I'm picking one person and two outcomes here are possible. Okay, like this, two different groupings, okay, 2 events. But I'm only choosing one person. See, if you notice all these things, choose a person at random. So the action is I'm actually just choosing one thing. In independent events is this, okay? I'm choosing 2 things, okay? I'm going to do 2 events. I'm going to do 2 actions, and I want both of them to occur. So I'm going to choose an A event, and then I'm going to choose a B event. So I'm actually doing 2 actions, and that's how I keep it straight. Hopefully you'll see this a little bit more clearly as we do some examples. And so forth. So here is the spinner one. All right. So a spinner, you're going to spin it 2 times. See, there's the action. I'm going to spin twice. Assume that the probability of a blue each time is 1/3, and the probability of red each spin is 2/3. What is the probability of getting the same color both times? Okay, so that's what we're looking at. So again, before we were choosing one student, and we wanted to see if they landed in multiple groups. Here I'm doing 2 actions. I'm spinning twice, and I want a certain outcome each time. So is this going to be independent or dependent? Okay. Each spin is independent of each other because it doesn't matter what I got on the first spin. That outcome does not change the fact that the blue is 1/3 and the red is 2/3. So the second spin is not affected by the first spin. So we need to find what is the probability of a blue and then a blue again, and then the probability of a red and then a red again. And then we're going to combine those together. Okay? So the probability of blue and blue, since they are independent of each other, it would be the probability of a blue times the probability of a blue, which is 1/3 times 1/3, which is 1/9. The probability of spinning a red, and then the probability of spinning a red again, is 2/3 times 2/3, or 4/9. Now, the probability of getting the same color both times, well, I can get either both blues or both reds. That is now a mutually exclusive thing. Okay? And so for that one, what's the probability of getting blue or red, also signified by saying the same color, is the probability of a blue and a blue plus the probability of a red and a red. And these are mutually exclusive, so there is no overlap. You can't be both red, and blue. So therefore, it's 1/9 plus 4/9, or 5/9. So that's kind of how that works. Okay. The next example, we're going to use a little bit different approach to finding the probabilities for these. Okay, 2 identical cookie jars are on the counter. Jar A contains 2 chocolate chip cookies and 2 peanut butter cookies. Jar B contains 1 chocolate chip cookie. You select a cookie at random. What is the probability that it is a chocolate chip cookie? Okay, so how does that work? All right, what do we have to do in this scenario to figure this out? Well, a Venn diagram would be kind of challenging to do. So, but I still want to see what's going on. So because there's a jar and then there's cookies in the jar, you can look at this as a 2-step approach. Okay. The first thing we have to do is you have to pick the jar, and then you have to pick the cookie. So what we also notice in here is when I pick the jar, there's not the same number of cookies in each jar. So one of the things that will help us figure this out is let's go through each action and figure out the probability. And we're going to use what's called a probability tree. And here's how it works. So our first choice here is, let's choose a jar. So what is the probability of choosing a jar? Well, when I pick the jar here, it's either A or B. I don't know what's in the jars, so just assume you don't know. So in jar, that's a 50-50 chance, so it's 0.5 for each of those. Okay? So then what? Well, if I choose jar A, there's 4 cookies in it. There's 4 things that can happen now. I can get a chocolate chip cookie or the other chocolate chip or a peanut butter or a peanut butter. And since there's 4 cookies in there, okay, in that jar, they are the same probability. So it's 0.25 for each of these things that are occurring. But in the last jar here, jar B, there is only 1 cookie. Okay? Since there's only 1 cookie, you have a 100% chance of picking that cookie if you chose jar B. So what this illustrates to us is that these are not equally likely to occur events, and so the tree makes it a lot easier to do. Okay? Finding the probability of each of these things as we go across is a multiplication aspect of things. So what is that times each of these items here? And when you do that, you'll find out you're going to get 0.125 for each of these. But this one right here is 0.5. Finding the probability of every outcome in a sample space, this is a probability distribution. So what is the probability that I will pick a chocolate chip cookie? Well, these are the 3 chocolate chip cookies right here. I found the probability of each thing. If I add up all of these numbers right here, I'm going to get a 1. That plus that is 0.25, 0.25, on all these numbers, and you will get the full probability of 1. Okay, and so then each of the cookies that are chocolate chip, we add those together, and you will get a 75% chance of pulling a chocolate chip cookie. Okay, so let's look at another event type that is related to independent. This is basically dependent events or conditional probability. Conditional probability, the probability that an event B will occur given that event A has already occurred. Okay, A is going to happen on the condition that B is going to happen on the condition that A has already happened. And we use this little symbol right here. It's the probability of B given A has occurred. Okay, so the probability of B given A has occurred is the probability of A and B divided by the probability of A. Okay, and so it's also similar to the one before, right here. If I just divide this right here by A, right? These are independent events, so probability of B is the full probability of A and B divided by A. In conditional, this is B given A. So it's very similar formula. So let's look at an example. This is the cookie jar revisited. Now we're looking at it a little bit differently. This time I'm going to say, given that a cookie chosen at random is a chocolate chip cookie, what is the probability that it came from jar A? Okay, so you already know that you got a chocolate chip cookie. So I'm asking, what's the chance that it came from A? So what do I do there? Well, we had a formula. Let's go ahead and write it out. So what is the probability that I'm going to have jar A given that a chocolate chip cookie was chosen? Well, then that's the probability of jar A and a chocolate chip cookie divided by the probability that it is a chocolate chip cookie. So what is the probability of a jar A and chocolate chip cookie? It's this one and that one. So add those together right there. Okay. So it's 1/2 times 2/4 Okay, remember probability of jar A and the probability of chocolate chip cookie there. And then this down here, given that this, we already know this is 3/4, I put it back into a fraction. So as you work this out, you're going to get 1/3 opportunity. So that's how that works. Let's look at another example. So membership in an AppSchool Pro provided in a table if a student is selected at random. So what is the table? All right, looks like I forgot to draw it over here, so I'll do it real quickly. We have a couple of after-school programs. We're going to have drama, we'll have science, we'll have art, and this is the total. And then down here we have classes. We'll have the sophomore, we'll have the junior, and we'll have the senior, and this is the total here. So sometimes if you have numbers and stuff and you have information, if it's organized into a table, we can use this knowledge to help us answer probability questions. And this is 8, 13, 18, 39, and then 17, 40, 58, and then 115. So once I have the table, then it's just a matter of using the table to help me answer and finding numbers that I have over here. Okay? What is the probability that a member of the art club is a junior? So remember, okay, probability is what we want to happen over all things that can happen. All right? So they're asking, what is the probability that a member of the art club, so in other words, art has occurred. I chose somebody from art, and I want them to be a junior. So how many art students are there? The total is right here. There are 58 art students. Okay? And how many are juniors? There are 16. So you can go right to that approach right there if you have all the information at the table. But what they're asking you to do also as a conditional is, what's the probability that it's a junior, given that they're in art? So that would be the probability that they are a junior and art. Probability that they are in art. The probability that you are a junior and in art. So 16. The total number of students possible are 115. So this up here is 16 over 115 total students. And then the bottom one is, what's the probability that you're in art? Well, there's 58 art students out of the 115. And so if I flip the bottom and multiply and all that kind of stuff, there's my 16 over 58. And you can go right to that one. Make sure you always reduce your fractions to the lowest possible. So in other words, what's the probability that you're in art and a junior? That's 16 out of 58. So we could have gone directly there also. What is the probability that a sophomore is a member of the drama club? So again, the same idea again. How many people are in drama? What's probably that a sophomore? I'm sorry, that we have a sophomore, okay, in drama. So there's 3 out of, I have the wrong number here somewhere. There's 36 sophomores, okay, and 3 of them are in drama. So that's how that one works. There's 36 total sophomores, 3 of them are in drama. But we can do it the other way also. What is the probability that you are in drama, given that you are a sophomore? And that's the way it's like that. Sophomore happened, 3 of them are in drama. Drama and a sophomore is the probability that they are a sophomore. And so we get the 3 out of the 115 total students, 36 out of the 115 total students gives me the 3 over the 36, which is 1/12. Which probably that a sophomore, so we've chosen a sophomore, or in the drama club, there are 3 sophomores in drama out of a total of 36 sophomores. Probability that you are in drama, given that you are a sophomore. Okay? All right, so let's look at some other. Before we can answer this question, we need to learn some more things. Okay, so here we go. A binomial experiment is an experiment that consists of a fixed number of trials with the following features. Each trial has two possible outcomes, one of which is denoted as a success. The results of the trials are independent events. That means each time we do it, it's independent. And the probability of success is the same for each trial. So in other words, the probability can't change each time I do a trial. All right. So this is following the binomial process, binomial theorem process. So binomial probability formula for a binomial experiment consisting of n trials with the probability of success p for each trial. The probability of an exactly r successes out of n trials is given by this formula right here. Okay, so the probability of however many successes I want are the ways to get r successes in n trials times the probability of r successes times the probability of n minus r failures. So how does that work? So this is the formula you're going to use right here. P is the probability of success. 1 minus P is the probability of a failure. So here's that NCR from our counting principles. Okay, and so you just use this formula right here, and you should be able to work this out and get your answers. So let's see this in action. All right, and that is what the last example is. All right, let me zoom out just a tad. So a grocery store gives away scratch-off cards with a purchase of more than $100. Joe has 5 scratch-off cards. What is the probability that he has exactly 3 winning cards if each card has a 30% chance of being a winner? Okay, well, the first thing is this a binomial experiment? So Joe's 5 cards, he's going to scratch off one at a time. So that's 5, can be represented as 5 trials. Each card is a winner or not. Okay, whether one card is a winner is independent if the other one is. So if he has 5 cards, they can all be winners or not. They're independent events. And the probability of a winning card is 30% no matter what. So yes, this is a binomial experiment. So since I want to have exactly 3 winning cards, I'm asking, what is the probability of 3 winners? So according to our formula, okay, it is NCR. So N is the number of trials. R is the 3. And our probability of a winner, so P is 0.3. That's the probability. So we have 5 choose 3. The probability of a winner to the 3rd power. The probability of a loser, and that would be to the 5 minus 3 or 2. So we need to work this out, and you can do this on a calculator. This will be 10. This will be 0.027, and this over here is going to be 0.49. And so you multiply all that together, and you're going to get 0.1323 or 13.23%. And so that's how you can do a problem like that. Okay, so we'll do more problems together in class, and so ends this video.